Okay, this is part 3 of the geometrics. We've looked at sequences, we've looked at series, and now we're going to look at infinity. Just be careful it doesn't look back. Okay, so the general idea behind this topic is what happens if we kept the series going indefinitely? What would all of those numbers add up to? Now, in this case, we've got a series 1, 2, 4, 8. We can say that a is equal to 1, and we can say that r is equal to 2. We can have a think about what happens with this formula. So Sn is equal to a, lots of 1 minus r to the n, all over 1 minus r. And in this particular case, we can fill in a as being 1 and r as being 2, and that would simplify to 1 minus 2 to the n. Probably don't need those brackets now. All over 1 minus 2, so all over minus 1, which we could simplify a little bit more, times in top and bottom by minus 1, I suppose, to be 2 to the n minus 1. Now what happens to that when n gets very, very large? Well, as n gets big, 2 to the power of n gets absolutely enormous. So like if n is 5, 2's already at 32. If n is 10, 2's up to 1024. So that sum is also going towards infinity as we're looking at larger and larger values of n. We call this a divergent series, because that sum is going to get really, really large. It's not going to tend towards anything. It's got no limits. So isn't that always going to be the case then? If we're adding an infinite number of terms, then isn't our sum always going to be infinite as well? Well, not always. So here's a situation where it's not. In this one, we've got a is 1 and r is a half, and we want to think about what happens to the sum to n as n gets really, really large. So our sum to n is going to be a, lots of 1 minus r to the n, all over 1 minus r. We can sub in that a is 1. We can sub in that r is a half. And we can tidy this up a little bit and take out the 1 and say, well, we've got 1 minus a half to the power of n all over a half. We could, I suppose, double it as well and say that this is 2 minus 2 lots of a half to the n all over 1. So that would just be 2 minus 2 lots of a half to the n. Now, what's actually going to happen to this? Well, as n tends to infinity, what happens to a half to the power of n? Well, a half to the power of 1 is a half to the power of 2 is a quarter, a half cubed is an eighth. It's actually getting smaller. And that process will continue. 1 over 2 to the n tends to 0. As n tends towards infinity, it gets very, 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 very small. So this sequence that we've come up with of 2 minus 2 lots of 0, essentially, this is going to tend just towards 2, take away 0, or just 2. So the limit of this sequence is 2, and it does exist. You can also think about this by thinking about squares is another way of doing it. If we think about these as like fractions of a square, if we've imagined that's our 1, that's an entire square, and then that's, let's fill in, then that's our half a square that we add on next, and then that's our quarter square that we add on next, and then that's our eighth. And you can see that you can add a half of what's left as many times as you like. You will never actually fill that entire second square, and so the limit of continuing this forever will again be that number 2. This is called a convergent series because it does tend towards some sort of limit. So what we need is a general way of telling if a series is going to be convergent or divergent, and coming up hopefully with a smarter way of finding that limit than having to rearrange all the algebra that's involved. So what we want to do is look at our formula and think, well, a is kind of fixed, r is kind of fixed, 1 minus r is fixed. The only thing that's going to change as n gets bigger is this r to the power of n. Now, what happens to that depends on how big r actually is. So we've got here our first condition, modulus of r is less than 1. Now what that means is that the size of r is somewhere between 1 and minus 1. And if you think about any number that's inside that range, it gets smaller when you increase the power. We saw that on the previous slide. If you add r was a half and you square it, it comes a quarter, cube it, becomes an eighth, etc., etc. It gets smaller. That's true for any number that's less than 1 or bigger than minus 1. So we can say here that if the modulus of r is less than 1, then r to the n is tending towards 0. So the opposite is obviously true for the third case, where r is greater than 1. So that means either r is greater than 1 or r is more negative than minus 1. Because when those numbers are raised to a power, they get bigger. So if r is greater than 1, we can say r to the n tends towards infinity. And the only one that's sort of weird is r equals 1. So that means either r equals 1 or r equals minus 1, because we're talking about the size. Because the size does not change. If you do 1 to the power of 100, it's still 1. So we can say that if the modulus of r is 1, then to the power of n is either 1 or minus 1. Now if we're thinking about which series will converge and which series will diverge, these ones are going to converge because that part of the formula is tending towards 0. These ones are going to diverge because these parts of the formula are tending towards infinity. And these third ones, these middle ones, are what we're going to call an oscillating case, where the numbers are going to sort of flick back and forth. And I'll show you an example of one of those in a sec. So what is our actual sum to infinity going to be? Well, let's look at this as the first one as a situation. We know that Sn is equal to a lots of 1 minus r. So our S infinity is going to be equal to a lots of 1 minus 0, because we said Rn tends towards 0, over 1 minus r. Can we tidy that up? Yeah, that bracket's just 1 minus 0 is just 1, so times a is just a. So our sum to infinity, and only in this first case, is a over 1 minus r. Now if we try to do the same thing for the divergent case, we'd end up with a sum to infinity is a lots of 1 minus infinity over 1 minus r, which makes no sense whatsoever, so can't be used as a formula. In the oscillating case, we run into the unfortunate issue that the formula ends up doing 1 minus 1 over 1 minus 1, which is a lots of 0 over 0, and dividing by 0 is a big worry. So you can't use this formula to predict sums for where the modulus of 1 is, where the modulus of r is 1 either. So here's that statement written up all nice and pretty. Let's actually try and use it with a few examples. So I've tried to pick out some ones that are a little bit awkward at least. We've got 8 minus 6, 4.5, etc. In this case, we are saying that a is equal to 8, because the first term is 8, and r is, I think, minus 0.75. So let's put that all into our formula. The sum to infinity here is equal to a, so 8 over 1 minus 0.75, so that would be 1.75. And so we would have 4.57 is apparently what that tends towards, ... For our second example here, we've got a is equal to 10 and r is equal to 0.11. So our sum to infinity will be equal to 10 over 1 minus that is 0.89. And we should get that that eventually becomes 11.23 ... That's fine. And then for our third one, well, we've got a is equal to 5 and r is equal to 1.6. So S infinity is equal to danger, danger. The modulus of r is not less than 1. So the sum to infinity does not exist. This is a divergent series. All right, let's finish off by looking at an exam style question. In this one, we're told S4 is 15. So let's write down that information. We know that S4 is equal to a lots of 1 minus r to the 4 all over 1 minus r, and we know that's equal to 15. We're also told S infinity is 16, so we know S infinity is a over 1 minus r, and that's equal to 16. Now, how are we going to combine these two together to get rid of something? I would probably rearrange them to make a the subject. So if I do that, I'll end up with 15 lots of 1 minus r over 1 minus r to the 4 from my first term. I'll end up with a equals 16 lots of 1 minus r from my second term. I'm then going to set those two things equal to each other, and hopefully something nice will happen. So we've got 15 lots of 1 minus r over 1 minus r to the 4 is equal to 16 lots of 1 minus r. You may be tempted to, I think, expand the brackets, but I'm going to hold off for just a second. I'm actually going to do a bit of a swap. I'm going to take the 1 minus 4 here and the 1 minus r here, and I'm going to divide by the 1 minus r and times by the 1 minus r to the 4. So I'll end up with 15 lots of 1 minus r over 1 minus r is equal to 16 lots of 1 minus r to the 4. Now, good thing with that is we can cancel out the 1 minus r's. We are allowed to do that because r is definitely not 1, because the sequence converges, and one of the conditions for convergence is that r does not equal 1. So we're not dividing by 0. From there, we can expand our brackets. So I'll get 16 minus 16r to the 4. We can subtract the 15 and add the r to the 4. So we'll end up with 16r to the 4 is 1. We'll end up with r to the 4 is a 16th. And so r is plus or minus a half. Now we're told all terms in the series are positive. So that means that r is going to be equal to a half, and that we want to find the first term. So that just means we need to sub that half into one of the formulas we worked out. We worked out here that a is 16 lots of 1 minus r. So let's put a half into that. 16 lots of a half. And that's going to give us 8. So our first term was 8. So in theory, the sequence should have gone 8, 4, 2, 1.5, etc. And yeah, the first 4 of those do add up to 15. Nice one.